Good morning everybody, hope you're all healthy and safe. So today we are going to move on to the next section of our third module, section 4.3, and in this module we shall be discussing, or in this section we shall be discussing about translation theorems. So why are we going to learn these translation theorems? Now we have seen the definition of Laplace transform. The Laplace transform was L of script L of f of t is nothing but the integral 0 to infinity e raised to st into f of t dt, right? So the Laplace transform, we can determine the Laplace transform of the given function f of t using this formula. But this is not always easy if the given function f of t is of some complicated form. Like usually integration gets complicated when we have to use integration by parts. That is itself is complicated. So when we have to apply or determine the Laplace transform of like multiple functions like t cube into e raised to 3t, if f of t is t cube into e raised to 3t, or if you can say that f of t is e exponential of 3t into t square into sine 3t, how will we determine the Laplace transform of these functions? It will get complicated, right? There will be lots of calculations to be done. So to make this Laplace transform, determination of Laplace transform of these functions, of these types of functions, of a bit complicated functions, much more easy, we shall be using the so-called translation theorems. So in the first translation theorem we shall be discussing about the Laplace transform of the exponential multiple of the given function. That is, we will be given a function, and if we are asked to find the Laplace transform of the exponential multiple of that function, then we can use this theorem. It is also known as the first shifting theorem. That is clear by the theorem statement itself. That is, let's look into it. If L of f of t is equal to f of s and a is any real number, then the Laplace transform of e raised to at into f of t is nothing but f of s minus a. That is the graph, or you can see that it is shifting to a. We get Laplace transform of f of t is f of s, and Laplace transform of e raised to f of t is nothing but f of s minus a. Okay, this is the first translation theorem or the first shifting theorem. The proof is very much simple, because you can just see what is L of e raised to at into f of t. This is nothing but integral 0 to infinity e raised to minus st e raised to at into f of t dt, right? Now what is this? This is nothing but 0 to infinity e raised to minus of s minus a into t into f of t dt, and that is our own f of s minus a. So there is nothing much proof in this theorem and all. This is just easily attainable. So this is how we use the Laplace first translation theorem, or which is called as the first shifting theorem. So let's just see a quick example which is given in your textbook, which depicts the same. That is, we are asked to determine what is the Laplace transform of the function e raised to phi t into t cube. Okay, whenever you see an exponential multiple, first of all determine what is script L of t cube. What is script L of t cube, or Laplace transform of t cube? It is nothing but 3 factorial by s raised to 4, right? So here the Laplace transform of e raised to phi t into t cube will be nothing but, this is our f of s, this will be nothing but f of s minus 5. Okay, so what will be the answer? F of s minus 5 is 3 factorial by s minus 5 whole raised to 4. Okay, so the Laplace transform of e raised to 5t into t cube is nothing but 3 factorial by s minus 5 whole raised to 4. This was the first one. So similarly, let's look into another example, that is the Laplace transform of e raised to 2t minus 2t into cos 4t. So first write what is our Laplace transform of cos 4t. This is Laplace transform of cos 4t will be nothing but s by s square plus 4 square, that is 16. So in this case our a is equal to minus 2, so our Laplace corresponding Laplace transform would be, instead of s we will have s plus 2, and here also we'll have s plus 2 whole square. Okay, so this will be the Laplace transform of our function e raised to minus 2t into cos 4t. So this is how we determine the Laplace transform of the functions of which are the exponential multiple of the given function. That was pretty much easy. Now for us, we'll be a little bit more concerned about the inverse form. Even the translation theorem is useful to determine the Laplace transform or to determine solve various differential equation, but mostly we'll be applying, you have as we have done to solve the differential equation, we have seen that to find the solution we usually apply the inverse transform, right? So the inverse form is also pretty much important. So from this, the inverse is the scriptal inverse of f of capital F of s minus a is nothing but e raised to at into f of t. So that is also an important formula or equation which we must keep in mind. So now let's move on to the examples and let's see how we can work out or how we can determine the corresponding differential equations solution and all. So the first one is determine the inverse Laplace transform of 2s plus 5 divided by s minus 3 whole square, right? So first of all, we'll have to use partial fraction to determine or to split this out. It is s minus 3 whole square is nothing but a by s minus 3 plus b by s minus 3 whole square. So this implies solving we get 2s plus 5 is equal to a into s minus 3 square plus b into s minus 3. Now solving, you can just work it out. We get a is equal to 2 and b is equal to 11. Okay, so our corresponding equation will become to determine the inverse Laplace transform of 2s plus 5 by s minus 3 whole square is same as to determine the Laplace transform of 2 by s minus 3 plus Laplace is linear, so you can directly apply this 11 by s minus 3 whole square, right? That is 2 into Laplace transform inverse of 1 by s minus 3 plus 11 into 1 by s minus 3 whole square. So this is all direct formula. S minus 3, that is s minus a, Laplace inverse of s minus a is nothing but e raised to 3t. So this is e2 into e raised to 3t plus here we have this is actually f of s minus a, where a is 3. So 1 by s square. What is the Laplace inverse Laplace transform of 1 by s square? It is nothing but t, right? So here instead of t we'll have to do the exponential multiple, that is e raised to 3t into t. I hope you are getting the concept. Okay, Laplace inverse of 1 by s minus 3 whole square. We know inverse of 1 by s square is nothing but t. So when we have 1 by s minus 3 square, applying the inverse form of the first translation theorem, we get the Laplace inverse will be nothing but t into e raised to 3t. Here a is 3. Okay, so keep this thing in your mind thoroughly. So this will be the Laplace inverse. You can simplify it. You can take e raised to 3t common, and this is 2 plus 11t. Okay, so this is the inverse Laplace transform of the given function. Now let's just look into another one, that is the inverse of s by 2 plus 5 by 3 whole divided by s square plus 4s plus 6. Okay, so here again we have to apply our partial fraction and all. So let's just see how we can proceed. We have s square plus 4s plus 6. This I can write this as like x square plus 4s plus 4 plus 2, right? So this is nothing but s plus 2 whole square plus 2, right? So the denominator is actually s plus 2 whole square plus 2, or it is like 1 by or some function s by s square plus say root 2 square, right? So the Laplace inverse will be either cos or sine depending upon the numerator. So but instead of s we have s plus 2. So the numerator instead of s we should be having s plus 2, and 5 by 3 is fine because it is into 1, so we can consider the expansion of our sign. Correspondingly we have to convert this s by 2 to some form in terms of s plus 2, right? So we have 1 by 2 or s by 2 plus 5 by 3 is nothing but half of s plus 2 plus 5 by 3 minus 1. That is, I'm just adding 2 by 2, then only we'll get s plus 2, that is adding and subtracting 1. Okay, so this is nothing but 1 by 2 into s plus 2 plus, what do we get, 2 by 3. Okay, that is I am changing s to s plus 2. So that is, instead of s I need s plus 2, so I'll have to add 2 by 2, right? It will be here, so 2 by 2 is 1, so I'll have to add and subtract that particular term. So I get this as s by 2, 1 by 2 s plus 2 plus 2 by 3. So what will our transformed, we are asked to determine L inverse of s by 2 plus 5 by 3 whole divided by s square plus 4s plus 6. This we have converted into the form 1 by 2 s plus 2 plus our 2 by 3 whole divided by s plus 2 whole square plus 2, right? This is how we have done it, right? So this I can write it as the Laplace inverse Laplace transform of 1 by 2 into s plus 2 whole divided by s plus 2 whole square plus 2 plus 2 by 3 by s plus 2 whole square plus 2, right? So this is 1 by 2 into script L inverse of s plus 2 by s plus 2 whole square plus, instead of 2 I'm just writing root 2 square. Okay, that is like s square plus a square form, plus 2 by 3 into I'll have to multiply and divide by root 2, so that will be into 1 by root 2 into script L inverse of root 2 by s plus 2 whole square plus 2 or root 2 square. So the first Laplace inverse is of our cos function, and the other one it is of sine function, right? So the value would be 1 by 2 into, and we have a shifting over there by a is equal to minus 2, so e raised to minus 2t into sine of or cos of, not sine, cos of root 2t plus 2 by 3 root 2, again there's a translation, e raised to minus 2t into sine of root 2t. Okay, or I can take e raised to minus 2t common, and I can write this as cos root 2t by 2 plus root 2 by 3 into sine root 2t. So this is our required inverse Laplace transform. So just keep in mind the shifting and just look into the problems carefully so that you can understand what is our shift happening and what is the Laplace inverse that we have to apply and all. Now in the next example we shall be discussing about solving the initial value problem, which is of our main concern. So the problem is to solve y double dash minus 6y dash plus 9y is equal to t square into e raised to 3t. So let's apply Laplace transform throughout. So we have, and we have to use the theorem, right? Laplace transform of y double dash minus 6 into Laplace transform of y dash plus 9 into Laplace transform of y is equal to the Laplace transform of t square into e raised to 3t. So while solving such initial value problems, okay, there's the initial values also given to us, that is y of 0 is 2 and y dash of 0 is 7. Okay, so solving such initial value problems, we'll have to use the first translation theorem as well as its inverse form also, because here we'll have to use a translation theorem, right? The exponential multiple of a known function. T square is a known function. We are applying the exponential multiple. So what will it be? What is the script L of t square? It is nothing but correspondingly it is 2 factorial by s raised to 3, right? 2 factorial by s cube. So instead of s we'll have a is 3, so we'll have s minus 3. So this is nothing but 2 factorial, which is 2 itself, 2 by s minus 3 whole cube. That is the Laplace transform of t square into e raised to 3t. Now here we'll apply the formula which we have learned in the previous section, that is s square into y of s minus s into y of 0 minus y dash of 0 minus 6 into s into y of s minus y of 0 plus 9 into y of s is equal to 2 by s minus 3 whole cube. Okay, so what is, we'll just simplify it. We'll take the terms of y of s common. So this is nothing but s square minus 6x plus 9 into capital Y of s minus, what is y of 0? It is 2, that is 2s minus 7 plus 6 into 2, that is 12. So that will be equal to this whole together is coming out to be 5, right? So this is equal to 2 by s minus 3 whole square. So when I just simplify it and keeping y of s only on one side, I get s square minus 6x plus 9 into y of s is equal to 2 by s minus 3 whole square whole cube plus 2s plus 5. Okay, so this implies this is nothing but s minus 3 whole square is equal to 2 by s minus 3 whole raised to 3 plus 2s plus 5. So this implies y of s is equal to 2 by s minus 3 whole raised to 5 plus 2s plus 5 by s minus 3 whole square. Okay, so now we'll apply the Laplace transform, right? Inverse Laplace transform. So applying inverse Laplace transform, we get y of t, that is L inverse of y of s, that is nothing but y of t will be equal to 2 times L inverse of 1 by s minus 3 whole raised to 5 plus L inverse of 2s plus 5 divided by s minus 3 whole square. So this was this Laplace transform was the very first example that we had seen, and we know that the value is correspondingly, this is equal to, so this will be equal to 2 into e raised to 3t plus 11 into e raised to 3t into t. That is the corresponding inverse of this. Now let's see what is here. Here we'll have to we have 1 by s minus 3 whole raised to 5. So here n is nothing but 4. So we have to multiply and divide by 4 factorial. So that will be equal to 2 by 4 factorial into Laplace L inverse of 4 factorial by s minus 3 whole raised to 5, that is nothing but t raised to 4 into e raised to 3t. So this will be the corresponding solution of the initial value problem which was given to us. Okay, so we shall see more examples, and we shall do more problems related to this which will help in understanding the concept a bit more clearly. I mean, actually there is not much of concept to understand. We just have to keep in mind the formula, that is the translation formula and the inverse form, and which will be used to solve the initial value problems. So we shall be doing more working out more problems which will make the formula which will keep the formula in our mind thoroughly. So don't get confused. So just recall all the Laplace transform of the well-known functions, and the first translation theorem is nothing but the Laplace transform of the exponential multiples of the well-known functions. Just practice on your partial fraction thing, how to separate the numerator and the denominator part. So that's it. So we shall stop here. So thank you all of you. Stay safe and healthy.